Hello viewers, today we are going to discuss signals and systems. Briefly, in signals and systems we will discuss first part signals and the second part systems. So, if we describe signals, any quantity having associated information with it is defined as signals. Signals can be understood as patterns. As an example, speech signals, whatever we speak signal, that is in between 300 hertz to 3.4 kilohertz. Audio signal, whatever we can hear in signals, the frequency lies between 20 hertz to 20 kilohertz. Video signals, whatever we can see in signals, frequency lies between 0 to 4.5 megahertz, etc. Other than these speech, audio and video signals, we can also think of electrical voltage and current signals. Electrical system, if we see in the slide, there is an electrical system. We are giving input, that is electrical input, and we are getting electrical output. So, both are signals, means signal going inside the system and coming outside the system. So, in system any operation can be done on the signal. So, signals need not be a function of time only, it can depend on number of variables. If signal depends on n variables, then it is called n dimensional signal. Now, we will discuss over here on different operation on a signals. What kind of operations we can do on signals. The different operations we can do on signals like time scaling, time shifting and time reversals. So, in the next slide we will discuss about time scaling. In time scaling, if we see x t, x within the argument t is given, t is time. If we scale in time, that is x within the argument, within the bracket you can say x a t. So, t, the argument which was there in the initial x of t, now is scaled to a of t. A is a constant. If a is greater than 1, then we are saying that we are compressing the signals. Compressing the signal means we are compressing in time scale. When a is less than 1, it means expansion, it means we are expanding the signal in time span. So, t tends to a t means divide by a for all instance of time. Suppose in the below figure, if we see x t is 1 between minus 1 and 1, if a is equal to 2, it means we are dividing by 2. So, t at 1 shifted to 1 by 2 and t at minus 1 is shifted to minus 1 by 2. It means x 2 t is now shrinking, means compressing in time scale. The same way, if we take a is less than 1, means a equal to 1 by 2, then t a t means t divided by 1 by 2 is nothing, again getting multiplied by 2. So, at t is equal to 1 is going to t equal to 2 and t is equal to minus 1 is going to t equal to minus 2. So, this shows the expansion of the signal. We can easily see in the figures given in the slide. If you see the example, x t is defined over here, x t is equal to 1 once t is in between minus 1 and 1 and 0 otherwise. If we scale it by 1 by 2, so x t by 2, so x t by 2 is equal to 1. If t by 2 is lies between minus 1 and 1, it means t is will be lying between minus 2 and 2 and 0 otherwise. The same way x 2 t again we have seen in the earlier slide, that will be compressing as 2 t is in between minus 1 and 1. So, t will be in between minus 1 by 2 and 1 by 2, otherwise it is 0. Next slide. Now, here in this slide we will discuss about time shifting. In time shifting means we are shifting the signal in time axis. The initial slides we discussed about time scaling, here we will be discussing time shifting. So, suppose x t, t is argument, now t shifted to t minus a. So, suppose a is greater than 0, then we will call the signal is delayed signal. If a is less than 0, then we will call the signal as advanced signal. So, t is equal to t minus a, what we have to do? Add a to all instants of time t equal to t plus a, subtract a from all time instants. As an example, suppose we have this signal x t, this is a triangular signal, it is going from it is in between t equal to 1 to 3. If you would like to plot t to t plus 5, it means we have to subtract 5. If you see over there in the arrow right side, x t plus 5 means we have to subtract 5. So, 3 minus 5 is minus 2, 1 minus 5 is minus 4. So, x t plus 5 is plotted. The same way, if we have x t minus 5, so it means we have to add 5. So, 5 plus 3 is 8 and 5 plus 1 is 6. So, once we subtract, this is left shifted, once we add, this is right shifted. Next slide, time reversal. We will discuss in this slide about time reversal, where if we replace t by minus t, then this is called time reversal. T is replaced by minus t and then mirror image around y axis. Suppose we replace t by minus t in any signal x of t, then we will only get the mirror image of the signal about y axis. So, if we see the again example x t 1 2 3, if we plot x of minus 3, then 3 will go to minus 3 and 1 will go to minus 1, and we can see from the figure also on the slide that this is a mirror image of the x of t. Transformation of signal. In transformation of signal, we will see the scaling and shifting operation altogether. So, in example, there is a graph x t. Now, we have to plot x of minus t plus 5 for the given signal. So, x of t, we can see on the figure x of t versus t. So, x t plus 5, x t plus 5, as we discussed before, so a is plus, then we have to subtract, right. So, if you have to subtract, then 2 minus 5 is 3 and 1 minus 5 is minus 4. So, minus 4 and minus 3, time shifting. Now, we again minus t is there. So, we have to apply time reversal. So, in case of time reversal x t by minus t, so the x minus t plus 5 will be the mirror image. Okay. So, in time reversal x minus t plus 5 is shown in the figure. Now, we will take an example where scaling and shifting both we have to do. So, what should be the order of scaling and shifting, whether we do scaling first or do shifting first, means what is the proper way of doing scaling and shifting. So, x t is given, as we have already seen x t in previous slides also. So, we have to find x 2 t plus 7. This contains scaling and shifting. Always perform shifting first followed by scaling. This means we have to first do shifting and then scaling. So, if we have to do x 2 t plus 7, so we will do x first x t to x t plus 7. We will shift in time axis and then scale. So, if we see over here, if we do t equal to t plus 7, it means again we have to subtract minus, right. 7 minus 2 is minus 5, 7 minus 1 is minus 6. Now, then after shifting t equal to t plus 7, we will scale the same by 2. So, if you will scale the by 2, it means again signal will compress in time scale, as we have already seen in the earlier slides. It means the new signal will be minus 2.5 and minus 3, because we have to divide minus 5 by 2 and minus 6 by 2. So, to get an expression of the form x a t plus minus b, it means either we are delaying the signal or advancing the signal, or we are scaling by a, then time shifting is done first and then followed by scaling. Next slide. Suppose we change the order, what will happen? If we change the order, means x t we are scaling first, so t will go to 2 t. So, this will be x 2 t. Now, if we do time shifting, then this will be x twice of t plus 7. So, it will be x twice t plus 14. This is not a right way of doing it, because your solution will be wrong. You can see if you solve it, it will be coming like minus 6 and minus 6.5. If we go to previous slide, then your solution was minus 3 and minus 2.5. So, what you have to do in this step, you take 2 common. So, it means you have to now shift by 7 by 2, right. So, if you multiply 2 into t plus 7 by 2, then it will be 2 t plus 7. So, this is the right way of doing it. Okay. So, if you are doing scaling first, then you have to take the factor common in which you are scaling, otherwise your solution will be wrong. So, what we have learned over here? We have learned over here that in case of scaling and shifting together, first we have to shift and then scale the signal. We will discuss about some special type of signals. There are some special type of signals. Those signals are like exponential signals, sinusoidal signals, unit impulse, unit step functions. So, in the next slide we will see exponential. Exponential signals, we already know that they are in the form of e to the power t or e to the power minus t, but over here I have taken a to the power t or for both the cases, right. So, if a is greater than 1, if you see the left figure, if a is greater than 1, we know for a is greater than 1, if we increase the power of any quantity which has greater than 1, then quantity becomes more and more and more. Suppose 2 is there, so 2 to the power 2 is 4, 2 to the power 3 is 8, but if a is less than 1, it means that is 1 by 2. So, if you increase the power of it, then it will be decreasing, right, it will be dying out. So, if a equal to 1 by 2, if you increase it by 2, 1 upon 2 to the power 2 is 1 by 4, 1 upon 2 to the power 3 is 1 by 8. So, this is decreasing. So, we can say this is decaying exponential and the left one is growing exponential. In the next slide, we will see sinusoidal signals. Sinusoidal signals, very comfortable. We always see these kind of things in maths like 12th class, sin x and cos x and sin x, right. So, generalized expression of any sinusoid is x t is equal to a sin omega t, where omega is equal to 2 pi by t and t is the time period, right. As we know, in the case of sin and cos, our time period is 2 pi and a is amplitude, omega is continuous time frequency, range of omega is from minus infinity to plus infinity and unit is radian per second. Please keep this thing in mind. Omega in continuous time domain, if we are discussing, then that is unit is radian per second. Next slide, unit impulse. Unit is impulse, if we discuss in continuous time, that is delta t, in discrete time, that is delta n. Delta t, as we see in the figure, at 0, that is delta t. So, delta t equal to 0 if t is not equal to 0, and delta t is not equal to 0 once t equal to 0. We cannot say delta t equal to 1 once t equal to 0. We will discuss it in the coming slide, what is the purpose of this delta t and what is the definition of delta t. Then delta n in discrete time, delta n everybody knows, delta n once n is not equal to 0, it is 0, but takes value 1 once n equal to 0. So, delta n is equal to 1. In the next slide, unit impulse. Delta t is not like other signal having unique definition, its definition is only generalized by using wide variety of signals. Okay. Delta t is equal to, if you see the rectangular pulse over there, the width of the pulse is a and the height of the pulse is 1 by a. So, if you compute the area of rectangle, what is the area of rectangle? Height into width. So, 1 by a into a is what? 1. It means limit a tends to 0, value of this rectangular pulse is 1. That is why we will again discuss in the coming slide what is the exact exact formulation of delta t. If you apply delta t minus t naught, if you are shifting by t naught, then the whole pulse is shifted by t naught towards right, and again if you compute the area over here, then the area will be equal to 1 at t equal to t naught. In the next slide, we will discuss properties of unit impulse. So, in the properties of unit impulse, area of unit impulse is 1 once minus infinite to plus infinite delta t dt is equal to 1, means area under the curve is 1. Any impulse which is defined at 0 minus and 0 plus means a infinitesimal width and infinite height, but infinite height we cannot see. So, this is the definition, area of unit impulse is 1 delta t dt is equal to 1. Delta t is present only at 0, or you can say 0 minus to 0 plus, hence integral value will only be 1 when it includes impulse. Okay. So, if you see the example, minus infinite to minus 2 delta t dt is equal to 0. Why? Because it does not include 0 minus or 0 plus. Okay. So, minus infinite to 3 dt delta t dt is 1. Why? Because this includes 0 minus and 0 plus. The same way 0 minus to 0 plus delta t dt is equal to 1. Why? Because it includes impulse at 0. The same way minus 4 to minus 2 delta t dt 0 does not include any 0. 3 to 5 delta t dt is 0. Why? Because this does not include 0 minus or 0 plus. Next slide, we will discuss about the properties of again unit impulse. If we scale the time delta, in place of delta t we are going to again put the argument bt, right, delta bt. So, delta bt is 1 upon mod of b delta t. You can ask the question, why delta b not b? I will give the answer in next line. So, once you plot 1 by mod b delta t, then delta b of t is equal to limit a tends to 0, again rectangular pulse, width is a by b, right. So, height is 1 by a, so area will be 1 by b. Okay. So, that is why delta b of t is 1 by mod b delta t, and delta minus t is equal to delta t. This is an even function, that is why we wrote 1 by mod b. You can write it delta minus b of t. So, delta b minus b of t, you can again take 1 by b delta minus t. So, delta minus t is equal to delta t. So, that is why this is always 1 by mod b delta t. Next slide, sampling property. If we multiply any signal x t with delta t minus a, then the value of x t delta t minus a will be x of a delta t minus a. It means the value of x of t will be the value of the signal at x t equal to a, that is nothing but x of a. So, minus infinite to plus infinite x t delta t dt, what is this? We can again, as delta t is only 1 once t equal to 0. So, minus infinite to plus infinite x 0 delta t, and x 0 now is a constant. So, take it out, x 0 minus infinite plus infinite delta t dt. So, this is x of 0. Now, there are two questions given, we will solve completely. First is minus infinite to plus infinite cos t delta t dt, and the second one is minus infinite to plus infinite sin t minus pi by 2 delta 3 t minus pi. So, over here the first one minus infinite to plus infinite cos t delta t dt, delta t will be 1 once t equal to 0. So, this will be cos of 0 1. B minus infinite plus infinite sin t minus pi by 2 delta 3 t minus pi dt. Now, delta 3 t minus pi is only non-zero at t equal to pi by 3. Why? Because once we put t equal to pi by 3, then delta 3 t minus pi is delta 0 and 1. But here you have to remember one thing, first take 3 common, otherwise you will make mistake. So, delta 3 t minus pi by 3, you take 3 t minus pi, take 3 common. So, 3 t minus pi by 3, now put t equal to pi by 3. So, this is 1 by 3 sin pi by 3 minus pi by 2. Sin pi by 3 minus pi by 2 is sin minus pi by 6, and sin minus theta is minus sin theta. So, this will be minus 1 by 3 sin pi by 6, and sin pi by 6 is 1 by 2. So, minus 1 by 3 into 1 by 2 is minus 1 by 6. In the next slide, unit step. Unit step function is defined ut is equal to 1 t greater than 0 and 0 t less than 0. Do not make mistake. Some of the books write ut equal to 1 once t is greater than or equal to 0. We cannot write this. Why? Because t, this u of t is discontinuous at t equal to 0, right. So, ut equal to 1 once t is greater than 0 and equal to 0 when t is less than 0. Because it is discontinuous at t equal to 0. So, ut plus a equal to 1 if t plus a is greater than 0 and 0 if t plus a is less than 0, or you can say ut plus 1 a equal to 1 if t is greater than minus a and 0 t is less than minus a. This function adds a step to the signal wherever required. Next slide, this is an example. Represent following signal as sum of shifted step signals. This is a very good example. You see very carefully that x t minus 3 to 0, minus 3 to 0, it goes the value from 0 to 4, right. Okay, it steps, right. 0, it steps again at 0 what? Minus 10, 4 minus 6, minus 6 means 4 plus 6 is 10, right. So, this is minus 10. Then again at 2 it steps up to minus 6 to 5. So, minus 6 to 5 stepping is 11. Then at 5 it comes from 5 to 0. So, step is minus 5. So, we can write this at minus 3 step of 4, 4 ut plus 3, at 0 step of minus 10, minus 10 ut, at 2 step of 11, 11 ut minus 2, at 5 step of minus 5, minus 5 ut minus 5. So, complete signal we can write it like x t is equal to 4 ut plus 3 minus 10 ut plus 11 ut minus 2 minus 5 ut minus 5. So, this signal can be represented using unit step functions. Then here now we will discuss types of signals. So, type of signals are, one way we can discriminate between signals, continuous signals and discrete signals. Continuous means signal's value is defined at each and every instant of time. In real life, the signals which we see are continuous in nature. Discrete signals, signal value is defined only for some specific instance of time, not every instant of time. Periodic and aperiodic signals, the left one which we see, if signal repeats itself after some time, then it is called periodic signal, and that some time or minimum time is called period of the signal. So, x t is equal to x t plus minus k t, where k is an integer and t is fundamental time period. Cos omega naught t, sin omega naught t, e to the power j omega naught t, these are the periodic signals where the period is 2 pi by omega naught. No time period, aperiodic. If the signals does not have any time period, then they are aperiodic. Whatever measured in terms of time for a continuous signal is measured in terms of number of samples for a discrete time signals. Okay. So, it means whatever we measure in terms of time for a continuous time signal is also measured in terms of numbers of samples for a discrete time signal. The next slide, for discrete time signals, the period is 2 pi by omega naught. This should be rational. Now, here in the period will be capital N, not capital T, because these are the numbers. So, minimum number of samples taken by a discrete time periodic signal to repeat itself is called its fundamental time period. So, they are the different numbers. If those numbers are repeating itself by certain amount of sequence n, then that is called periodic sequence, and the length of that sequence for which this is periodic is called period of the sequence. So, suppose we are taking e to the power j pi n. So, magnitude of e to the power j pi n is 1 and angle is n pi. So, suppose n equal to 2, then 2 pi by omega naught 2 pi by omega naught will be 2 once omega naught is equal to pi. So, 2 pi by pi. So, if you see in the right figure n equal to 0, then n equal to 1, then if n equal to 2 again will fall on n equal to 0. So, this will keep on repeating with the period of n equal to 2. The same way in the slide e to the power j pi by 4 n, here omega is equal to pi by 4. So, n will be equal to 8. So, now the whole 2 pi will be divided into 8 with the angle pi by 4. So, n equal to 0, then 1, 2, 3, 4, 5, 6, 7, again n equal to 8 will be the same value as n equal to 0. And over here omega naught is a discrete time frequency, and the over there in continuous time signal the range was minus infinite to plus infinite. Here the range of the frequency is minus pi to plus pi, and unit is radian per sample. Next slide, periodic. Again this is the same periodic and aperiodic. Here if you see cos omega naught, sin omega naught, e to the power j omega naught, conditionally periodic 2 pi by omega naught should be rational. What does it mean? It means 2 pi by omega naught into r is equal to n, and n should be an integer. So, what should be r? Minimum possible integer to make capital N is an integer. Okay. In the next slide, some of the periodic signals, some of the two periodic signals will be periodic only if ratio of their time period is rational. It means x1 t is periodic with period t1, x2 t is periodic with period t2, then t1 by t2 should be rational for periodic, and t1 by t2 is irrational, then signal is aperiodic. So, fundamental time period will be the LCM of t1 and t2. We can easily see in the given example, if x t is equal to 10 plus 8 cos pi by 7 t plus pi by 6 plus 5 cos pi by 6 t plus pi by 4 plus 3 cos 6 pi by 5 t plus pi by 3. If you see the period t1 for first component 10 is DC. So, there is nothing like that, this is a constant. The second over there we are mentioning as period t1. So, 2 pi by omega, 2 pi by 7 is 14, t2 2 pi by 5 pi by 6 12 by 5, then t3 2 pi by 6 2 pi divided by 6 pi by 5 is 5 by 3. So, the overall the LCM of all three will be 420. So, the period will be 420. Even and odd signals. Any signal which is even if x of t is equal to x of minus t, as the example cos t and delta t. Odd signal x of t is equal to minus x of minus t, sin t is an odd signal. We can break any signal in even and odd parts. So, if you want to break the any signal in even and odd parts, x even t is equal to x of t plus x of minus t by 2, and x odd t is equal to x of t minus x of minus t divided by 2. If signal is complex, then x of minus t is replaced by complex conjugate of x of t. Then this is an example, x t is given, the signal in right hand corner. If you want to break this in even and odd parts, then you can see in the below, red one is odd part and blue one is even part. If we add even and odd part, then the signal will become x of t. Energy and power signal. Energy in continuous time, energy is defined as minus infinite to plus infinite x square t dt, and power is defined as p is equal to limit t tends to infinite 1 by t over the period x square t dt. So, power is always computed over the period. The same way for discrete signals, energy you just replace integration with summation n equal to minus infinite to plus infinite x of n chi square, and p equal to limit n tends to infinite 1 by 2 n plus 1 n equal to minus n to plus n x n mod square. Signals having finite energy for which signals average power is 0 called energy signals. We go for power calculation when energy becomes infinite. Signals having infinite energy but finite average power are called power signals. X t goes to 0, S t goes to infinite are finite durations are energy signals, x t goes to 0, S t goes to infinite are periodic signals are called power signals. So, this is some examples. If you see the first signal t goes to infinite, x t is finite, this is power signal. Second signal t goes to infinite, x t goes to 0, energy signal. If third figure, if you see x t goes to infinity, s t goes to infinity, it means that is neither power signal nor energy signal. The simple note over here, periodic signals are always power signals and their power is calculated for one time period. This is end of unit 1. Overall, if we summarize the lecture, broadly we have discussed continuous time signals, discrete time signals and different kinds of signals and properties of the signals. I hope you enjoyed the lecture. Thank you very much.